Hello grade 10 students. Today I am here to teach you chapter 30 in your textbook, that's called probability. So what is probability? Probability is how likely something is to happen. I can take today it might rain. In the election time, which party will win the election? So we are not sure. So we'll see what are the main important definitions in probability now. Now we'll look at what are random experiments are. Now if I say one student get up, we are not sure who will get up. If I say Kevini, you get up, that means she knows that she has to get up. So it's sure that Kevini has to get up. So we say if you are not sure who will stand up or get up, that means there's an uncertainty. So those events are called random experiments. Another experiment, when you flip a coin, we don't know which side will appear. It might be head or it might be tail. So those events are called random experiments. So what are random experiments? We have uncertainty which will occur. So flipping a coin, we don't know. It can be heads or tails. Throwing a die, we don't know. It can be 1, 2, 3, 4, 5, 6. 6 numbers are there in a die. So we are not sure about those experiments. So those are called random experiments. Now we'll see what are sample space. So sample space is all possible outcomes of a random experiment. So we have to consider all possible outcomes. So we use capital S for sample space. Now how can we write down? There's a way of writing down sample space like a set. So we can write, think about tossing a coin or flipping a coin. What are the possible outcomes? You can get heads or tails. So we can write, instead of writing like this, I can write capital S is equal to, inside curly brackets, I can write down the elements or outcomes. So what are the outcomes? Heads or tails. I can put H instead of heads, tails, T. So this is how we write down the sample space. If I say throwing a die, what are the possible outcomes? I can write the sample space S is equal to, within curly brackets, I can write 1, 2, 3, 4, 5, 6. Don't repeat the same outcome. And in an exam, what are the possible outcomes? You can pass the exam, you can fail the exam. So in an exam, You can pass or fail. So what's the sample space? Pass or fail. When you take a cricket tournament, what are the possible outcomes? Cricket tournament. This can be, you can win the game or lose the game or maybe tie. So you get 3 possible outcomes there. So you need to know how to write down the sample space properly. All possible outcomes. Now we'll look at what are events. So events are a subset of a sample space. A subset of a sample space. Now we'll take example, 4-sided tetrahedral die. 4-sided so there are 4 sides, 1, 2, 3, 4. So what's the sample space? S can be 1, 2, 3, 4. Now if I want to get only 1 and 2 events that you get 1 and 2, so I can label as another event A is 1, 2. Or if I want another event like getting 1, I can label it as B getting 1. Or getting 1, 2, 3 less than 3. C number less than 3. Number less than 3. So what are the possible outcomes if it's less than 3? 1 and 2. So these all are subset of a sample space. So we call this is event A, event B and event C. Now we can divide any event into 2 parts. Any event into 2 parts. Simple events and composite events. So what are simple events? When you get only one possible outcome, we call those are simple events. Only occur one possible outcome. So here B is a simple event. I can write B getting 1 is a simple event, or getting 2 is a simple event. I'll label as D. Getting 2. Getting 4. E is an event. Getting 3. And also you can get 4 also. So I'll take as F. Getting 4. So these are only one possible outcome. Those are simple events. Then what are composite events? Events that occur 2 or more possible outcomes. So we'll take G is an event getting 1, 2, 3. Or I can take this one, A. Event A is getting 1, 2. So you need to know when you take any event, identify is it a simple one or a composite one. Now we'll see what are equally likely outcomes. If the chances of getting the outcome is the same, we call those are equally likely outcomes. Chances of getting outcomes are the same. Now we'll take tossing an unbiased coin. Tossing an unbiased coin. That means when you toss a coin, you get two sides now, heads or tails. So probability or the chance of getting head is the same as getting tail. Chance of getting head is the same as chance of getting tail. We call this is equally likely outcomes. Another example, consider two bags or one bag. Consider one bag with different colored marbles. Different colored marbles. Red, blue, yellow. If the chance of getting red is equal to the chance of getting blue, or if it's equal to the chance of getting yellow, we call these outcomes are equally likely. So I can write chance of getting red one is equal to the chance of getting blue one is equal to the chance of getting red color marble. We call these are equally likely outcomes. Now we'll see how we can calculate the probability of an event. So what's the symbol we can use? We can take capital P for probability. So in previous lesson also we used P letter. Can you remember for perimeter we use capital P. Here also we use probability, but we take P and then use brackets to identify the event. This is how we write down probability of a number. Now if we take the subset of getting A. A is an event from the sample space and the probability of getting A. We can write PA. Probability of getting event A. That's PA. So how can we calculate the probability? If we can find out number of elements in A, divide by the total number of elements in the sample space, we can calculate the probability. So what's the probability? Think about any event A. That's Probability of A is equal to number of elements in A over total number. Total number is number of elements in the S. S means sample space. So we'll write this means number of elements or outcomes in A. Here NS means number of outcomes in sample space. So when you take this number is always a small number less than 1. So you need to remember when we are calculating probability values lie between 0 and 1. You can get a fraction or only the whole number 1. If you get 2 or 3, something like bigger number, that means there's a calculation error. So remember this formula. I'll highlight that in red. This formula. You have to remember how we calculate the probability. Number of elements in any event divided by the total number. Total number means number of elements in the sample space. Now we'll take example number 1. With reference to an experiment in which a card is drawn randomly from a bag containing 5 identical cards numbered from 1 to 5. Write the sample space and find NS. What is NS? Number of elements in the sample space. So we'll take the first part, write down the sample space. So S is equal to, with curly brackets, you have to write down the outcomes. What are the numbers? Numbers from 1 to 5. 1, 2, 3, 4, 5. That's the sample space. Then what is number of elements in this sample space? You count the numbers. 1, 2, 3, 4, 5. 5 numbers are there. So number of elements in the sample space is 5. Then write down the elements of A and find NA if A is the event of getting an even number. So it's a subset of the sample space. Event is a subset of the sample space that's given as getting an even number. So how can we find out probability of getting an even number? How can we find out the elements or outcomes? What are the even numbers here? 2, 4 are the elements in even set. Then find out NA, number of elements in A, you get 2. Then third part, find the probability of A that an even number is drawn. Probability of A. So what is probability of A? Number of elements A over number of elements in the sample space. What is NA? NA is 2 and NS. NS is 5. 2 over 5. Example 2. In an experiment of rolling an unbiased die with its faces marked 1 to 6, find the probability that the number shown is 4. So when you take this one, unbiased die, sample space is 1, 2, 3, 4, 5, 6. Find the probability that the number shown is 4. Now we'll take any event is only getting 4. That's a simple event. Then they are asking what is probability of getting A. So to find out probability of A, we need NA over NS. But from this we can find out NS. 1, 2, 3, 4, 5, 6. We can find NA using this. Just one element. Then what's the probability? Probability of getting A is equal to 1 over 6. Then the next one, find the probability that the number shown is odd. We'll take a letter B for that. B is odd number. What are the odd numbers there? When you take 1 to 6, 1, 3, 5. Then what's the probability of getting B? NB, number of elements in B divided by number of elements in the sample space. So what is NB? 1, 2, 3. 3 numbers are there. So calculate the probability. 3 over, altogether 6 is there. 3 over 6 you can simplify further. That becomes half. Then the last part, find the probability that the number is greater than 2. We'll take that one as C, number greater than 2. Number greater than 2. What are the numbers greater than 2? 2 is not included. 3, 4, 5, 6. What's in C? Number of elements in C? 1, 2, 3, 4. Then calculate the probability. Probability of C is NC, number of elements in C divided by number of elements in the sample space. NC is 4 over, altogether 6 is the sample space. Simplify. 2 times 2, 2 times 3, you get 2 over 3. Take exercise 30.1. First question, write down the sample space for each of the following random experiments. First one, recording the card drawn from a pack of 10 identical cards numbered 1 to 10. So we'll take any event A. A is numbers 1 to 10. 1, 2, 10. But we can take this one as a sample space, not A, because we are taking the whole thing. I can take as S. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it says a circular disc. Second one is another example. A circular disc is divided into 3 identical sectors, one of which is colored red, another blue and the other yellow. A pointer is fixed to the center of the disc and the disc is spun. The color of the sector at which it stops is recorded. That means something like this. There's a wheel and divided into 3 identical sectors, equal parts. Equal parts means 120 each. So one is red, blue and yellow. and there's a pointer fixed, something like this, fixed. And when it's spun, what happens? You get a color, random color. So they are asking, what's the sample space here? So these are the all possible outcomes. What are the colors you can get? Red, blue, and yellow. So that's how we write down the sample space there. Third part. Recording the number of runs scored by a batsman in a single delivery in a cricket match. So what's the sample space? So sometimes you don't get any runs, so you can get 0, or you can get 1 run, 2 runs, 3 runs, and 4 straight away you can get 4 runs, and 6 runs, and 5 is a special case. How can you get 5? You can get 4 runs with no ball, you can get 5 runs. So we'll include 5 also. So what are the possibilities you can get in single delivery? You can get 0, 1, 2, 3, 4, 5, 6. Question number 2. Determine whether each event given below is a simple or a composite event. When rolling a tetrahedral die numbered 1 to 4. So, what's the sample space? First, you have to identify the sample space. 1, 2, 3, 4. Getting the number 3. We'll take A. Getting number 3 means you can just take 3. Just one possible outcome. So what's the event? A simple event. Now we'll take the next one. B. Getting a side with an odd number. So I'll label this as B. Getting odd number. What are the odd numbers you can get? You can get 1 and 3. So what's this event? A composite event, because you get 2 outcomes. Now we look at the next one. Second one is another event. In a pack of 5 identical cards labeled A, B, C, D, E. So what's the sample space? You can get A, B, C, D, E. And what's A? Part A, drawing the card labeled A. So I'll take any event C. I'll take another letter because A, B, C, D, E also here. I'll take G. G is the event getting A. So only one possible outcome. So we can say this is a simple event. We'll take the next one. B. B is drawing a card labeled with a vowel. We'll take as H is that event. Vowel. What are the vowels here? 1, 2, A, E, I, O, U. A is there. E is there. Now you are getting 2 outcomes. 2 outcomes means that's a composite event. Question number 3. When randomly taking a card from a bag containing 8 identical cards numbered 1 to 8. So first identify the sample space here. Card numbered 1 to 8. 1, 2, 3, 4, 5, 6, 7, 8. Part A. If the event of getting a card with a number greater than 4 is A. A is number greater than 4. Write down the elements in A. What are the elements? Greater than 4 means not included 4. We can write 5, 6, 7, 8. Then the third part, it says, write 5 simple events in the event A. Can we write down 5? Simple events means you can get only one possibility. So we can take as any letter. B can be getting 5. C can be getting 6. D can be getting 7. And E can be getting 8. So we can write only 4 simple events. You can't write 5 there. Question number 4. There is a bag containing 10 identical pieces of paper numbered from 1 to 10. A piece of paper is drawn at random. Write the sample space. So, what's the sample space? You can get numbered 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the sample space. Then, if the event of drawing a square number is x, x is square number. Getting a square number. What are square numbers? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So 16 is not there. So 1, 4, 9. So write down the elements of x. So that's x. And find out nx, number of elements in x. 1, 2, 3. So 3 is the answer. Part 3, find the probability of getting a square number. So what is px? Probability of getting x is nx over ns. Nx is number of elements in x, that's 3, divide by total number of elements. Here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ns is 10. So we'll substitute here. So the answer is 3 over 10. Question number 5. 3 of 5 identical beads are blue. Blue ones are there and red. 2 are red. A bead is drawn randomly. Write the sample space. Okay, so when you take this one, there are 5 beads now. 1, 2, 3, 4, 5. We'll label 3 blues as B1, B1, B2, B3. And 2 red ones are there. 2 red ones I'll take as R1, R2. Then I can easily write down the sample space. So in the first part it says write down the sample space. I can write down B1, B2, B3, R1, R2. So that's the sample space. Then find out the probability of drawing a red bead. Probability of getting a red bead. How will you find out? Number of red beads divide by the total number. That means NS. NS we know 1, 2, 3, 4, 5. So you get 5 as the denominator. How many reds are there? R1, R2. So you can get the probability as 2 over 5. Third one, find the probability of getting blue one. So blue one is equal to number of elements of getting blue over number of elements in the sample space. How many blues are there? 1, 2, 3 now. 3 over 5 is the answer. Question number 6. There are toffees of the same size and same shape but of different brands in a box. The table below gives information on them. A toffee is drawn randomly from the box. Find the probability of getting. First one is an orange flavored one. So I'll write probability of getting an orange flavor. All together, when you take this table, what's the total of mango flavored ones? 2 plus 3, you get 5. Orange flavored ones, 1 plus 2, you get 3. This way, brand A, how many toffees they have taken? 2 plus 1, 3. 3 plus 2, 5. And all together, they have taken 8. 3 plus 5, 8. 8 toffees are there. Out of 8, so you can write down, if you are writing the sample space, how can we write down? This is brand A, mango. Brand A, orange. Brand B, mango. Brand B, orange flavored ones are there. All together, 8 number of toffees are there. So we know that's in S is 8. Now we'll count how many elements in this one, orange flavor. So they are not particular about the brand, only orange flavored ones. How many orange flavored ones altogether? 3. So N orange flavor divide by NS. Altogether 3 orange flavored ones out of 8. So the probability is 3 over 8. Second part, a toffee of brand A. Brand A, how many toffees they have taken? 3. So probability of brand A is equal to number of elements in brand A divide by NS. Number of elements in brand A is 3. So 3 over 8. Now the third part, a toffee of brand B. How many toffees in brand B? When you take this one, 5 toffees are there. So what's the probability? 5 over 8, because number in brand B is 5. Fourth part, a mango flavored toffee of brand A. Now they want mango flavored one, brand A. Now we'll see how many mango flavored of A. So mango flavored A is just 2 toffees are there. So 2 over 8. You can simplify and write down 1 over 4. Now take the next part. Part 5. An orange flavored toffee of brand B. Orange flavored of brand B now. Look at brand B. You need orange flavored ones. That's only 2. So 2 over 8. When you simplify, you get 1 over 4. Now we'll look at what's the intersection and union in probability. For that, we'll take this example. There are 5 identical balls numbered 1 to 5 and 1 is picked at random. If we denote the event of picking a ball with a number greater than 2 as A, we'll take, what's the sample space here? 5 identical balls numbered 1, 2, 3, 4, 5. And the event A is given a number greater than 2. Number greater than 2 means, what are the numbers? You can get 3, 4, 5. And there's another event, B. B is given as numbered an even number. Even number is set B. What are the numbers then? 2, 4. Now we'll try to find out the intersection and union from this. Okay, so here first we'll take intersection A intersection B. You know the intersection sign. U upside down. What's intersection means? Common for both A and B. Are there any common outcomes? Yes, 4 is common. Then union. Union means everything in B as well as everything in A. What are the elements in A and B? You get 2, 3, 4, 5. Those are the elements in A union B. Now we'll try to find out a connection between these. I'll take probability of A intersection B first. What's the probability of A intersection B? All together 1, 2, 3, 4, 5. 5 elements are there. 5 outcomes. NS is 5. What's NA? NA is 1, 2, 3. What's NB? 1, 2. NA intersection B? 1. NA union B is 1, 2, 3, 4. So what's the probability of A intersection B? NA intersection B over NS. 1 over 5. That's probability of A intersection B. Now we'll calculate the probability union. Probability of A union B. What's the probability? N A union B over N S. A union B is 4. 4 over 5. Now, what's the probability of getting A? I want what is probability of A now. I'll do it here. Probability of getting A. Three over 5. And what's the probability of getting B? B is 2 over 5. Now we need to find out the connection between these 4 probabilities. What can we find out? Can you see when you add these two, 3 plus 2, 5, 5 over 5. And when you subtract this one from that, what you get? 5 over 5 minus 1 over 5, you get 4 over 5. So we see a connection between all these probabilities. What we see? We see you can get the union value. A union B is equal to 4 over 5 is equal to probability of A plus probability of B minus the intersection is same as probability of A union B. So this is a formula that you need to know. Now we got a formula. What's the formula we got from the previous example? We found out probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Can you remember a similar formula we got in sets? Now, the relationship between number of elements in intersection and union. In previous section, we found out in A union B is equal to NA plus NB minus NA intersection B. That's the relationship between number of elements in sets, union as well as intersection. Now I want to divide the whole equation by NS. What is NS means? Number of elements in the sample space. So I'm dividing all these terms by NS. What you get? What is this one divided by this? That's the probability. Definition of probability. Probability of A union B is equal to, this is probability of getting A. Probability of getting B minus probability of getting A intersection B. So either from the set notation you can get this formula or from an example. So you need to remember relationship between elements in the union and the intersection. So we can switch these two as well. You can, if you want the intersection, how can we write down? You can write down this one here and this one as it is, and then this becomes union. So remember this formula. Now we'll look at what are mutually exclusive events. Events can't occur together. Can't occur together or at once. When you take a cricket match, we can't win as well as lose. We have to consider only one, either winning or losing, or it can be tie. So we can't take both at once. So those are mutually exclusive events. So when you take a coin, you can get either heads or tails, but you can't get both at once. That's also an example for mutually exclusive events. So what are mutually exclusive events? Can't occur at once. So I can write, for example, getting one or getting heads and tails at once. Or I can write in a cricket match, you can't win or lose at once. Now we'll see if the two events are mutually exclusive, what's the relationship between intersection and union. Now when you draw the Venn diagram for two events A and B, we say mutually exclusive means cannot happen together, there's no intersection. So this can be A, this can be B. So no intersection between these two means what's the probability of A intersection B? You get nothing. So nothing means 0. And what can you say about these two events? Two events are mutually exclusive means it's empty set. There are no elements in the intersection. So that's intersection is null and therefore the probability is 0. Now can you remember we got a formula before? Probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. For mutually exclusive, this becomes 0. This part becomes 0. So what happens to the formula? If the two events are mutually exclusive, we can write the union is equal to probability of A plus probability of B. Only when the two events are mutually exclusive. So I'll write down if the two events are mutually exclusive, you can use this formula. If the two events are normal events, then you can use the previous formula. Complement of an event. Can you remember? Complement means not belongs to that set. So if A is an event, complement we can label as A dash. Now we'll take an example. We'll take 5 identical cards. Example, 5 identical cards numbered 1 to 5. So that's the event and we'll take A as getting an even numbered card. Okay, so we'll write down the sample space. S is 1, 2, 3, 4, 5. Then what is NS? Number of elements in the sample space. You get 5. Now A is denoted by getting even number. What are the even numbers you can get? 2, 4. So what is NA? Only 2 outcomes are there. Now we need to find out complement of that. Complement of that means A dash. What's the definition? Not an even number. Not an even number means what are the numbers? The other numbers. So not an even number means 1, 3, 5. Now what is NA dash? You get NA dash is 3. Now we'll find out the probability. We'll find out the probability of that. Probability of A. Probability of A is 2 possible outcomes out of 5. And what is probability of A dash? 3 outcomes out of 5 outcomes. Now we'll see what's the relationship. If you take probability of getting the sample space, what you get? 5 outcomes over 5. See what's the relationship between these three. 2 over 5 plus 3 over 5, we get 5 over 5. So we can write, by looking at these three probabilities, I can write probability of S is equal to probability of A plus probability of A dash. So if I want to take 1 as a subject, I'll take PA as a subject. I can write PS minus PA dash. Or if I want PA dash, how can I write? I can write as PS minus PA. So you need to know this relationship as well. So what's the relationship between the complement of an event with the sample space? So either this or this. If you want the probability of getting an event, you can use this formula. So what is PS? We know 5 over 5. 5 over 5 is 1. So we can replace PS as 1. So I can rewrite this formula. Again, PA is 1 minus PA dash, or PA dash is equal to 1 minus PA. So I'll write why. What's the reason? PS I can write as 1. So remember this formula. Example number 1. For the event A and B of a random experiment, PA is given, PB, PA intersection B is given. You are asked to find out first part, that's A union B. So what is A union B? From the previous formula, we know that's A plus probability of B minus probability of A intersection B. Now, we'll substitute those values. PA is given 2 over 7, PB is 3 over 7, and A intersection B is 1 over 14. So, convert to the same denominator. I can convert to 14 is the common denominator. This becomes 2 times 2, 4, 3 times 2, 6, minus 1. You get 10 minus 1 is 9 over 14. Second part, probability of A dash. What's the relationship between probability of A dash and probability of A? We know that this is equal to 1 minus probability of A. 1 minus probability of A given as 2 over 7. 1 I can write 7 over 7 minus 2 over 7. That becomes 5 over 7. Third part, probability of B dash. Again, this is complement of B. That's equal to 1 minus probability of B. 1 minus probability of B is 3 over 7. I can write 1 as 7 over 7 minus 3 over 7. That becomes 4 over 7. Now the fourth part, probability of A intersection B whole thing dash. Again, this is a complement of an event. I can write as 1 minus probability of A intersection B. What is intersection? Intersection is 1 over 14. So 1 minus 1 over 14, I can write 14 over 14 minus 1 over 14 becomes 13 over 14. And the fifth part, probability of A union B whole thing dash. Again, use the same formula. Any complement event is equal to 1 minus the event. A union B, we found out union B is 9 over 14. So 1 minus 9 over 14. 1 I can write 14 over 14 minus 9 over 14. So what's the answer? 5 over 14. Example number 2. X and Y are two mutually exclusive events of a random experiment. Px is 1 over 6 and Py is 7 over 12. You are asked to find out the intersection. We know that mutually exclusive means no elements in common. So what's the intersection then? X intersection Y is 0. The probability of X intersection Y is 0. Second part, union. What's the formula for union? Union is equal to probability of X plus probability of Y. Here the intersection is 0, so you are not writing minus intersection there. If the two events are mutually exclusive, the union is equal to this. I can substitute the values 1 over 6 plus 7 over 12. Convert to the same denominator, 12. This becomes 2 plus 7, 9 over 12. Simplify. Divide by 3 here, you get 4. So 3/4 is the answer. Exercise 30.2. First question. In a random experiment of rolling a fair die numbered from 1 to 6, let A be the event that a prime number is obtained. So A is prime. What's B? B be the event that perfect square is obtained, a square number. What's C? C be the event that a number greater than 4. And D is an event that a multiple of 6 is obtained. Select all pairs of mutually exclusive events. Okay, so we'll see what are the elements first. So what's the sample space according to this question? S is given 1, 2, 3, 4, 5, 6. Out of that, what are prime numbers? Prime numbers are numbers not divisible by any other number, only divisible by 1 and itself. So what are the prime numbers? 2, 3 and 5. Square numbers, 1 squared is 1, 2 squared is 4. 1 and 4. Greater than 4. Greater than 4 means 4 is not included. 5 and 6. And multiples of 6. Multiples of 6, 6, 12 like that. So only 6 is there. Now we'll see what are mutually exclusive events means. There are no common elements for those events. When you take these two, A and B, we can see no common elements. I can write A and B are mutually exclusive. What are the other elements that are mutually exclusive? We can't take A and C because 5 is common. A and D, no common elements. I can write A and D also mutually exclusive. What else now? B with C, 1, 4, 5, 6. B with C also mutually exclusive. B with D, no common elements. I can write B with D as well. B and which one? B and D. Then C and D, you can't take because 6 is common. So these are the mutually exclusive events. Question number 2. Let X and Y be two events of random experiment which are not mutually exclusive. Probability of X is given 1/4, probability of Y is 5/6 and intersection is given 1/6. Find each of the following. First part is probability of X intersection. Here, can you see there's an error? This should be union. X union Y. Now we know what's the formula for union? Probability of X plus probability of Y minus probability of X intersection Y. Now substitute the values. 1/4 plus probability of Y is 5/6 minus 1/6. So when you simplify, you get 4/6. Simplify again, 1/5 plus 4/6 divide by 2. You get 2 here and 3. What's the common denominator of 4 and 3? You can convert to 12. 3 times 4 is 12. So 3 times 1. Here 4 times 3, 12. 4 times 2, 8. So 8 plus 3, you get 11. 11/12. Px dash. From the formula we know that's 1 minus Px. What is Px? Px given 1/4. I can write 1 as 4/4 minus 1/4 is equal to 3/4. Py dash. Again same thing. 1 minus probability of Y. 1 minus probability of Y is 5/6. I can write 1 as 6/6 here. Minus 5/6 is equal to 1/6. Probability of X intersection Y dash. What's the formula? 1 minus probability of X intersection Y. What's intersection? 1/6. 1 minus 1/6, that becomes 6/6 minus 1/6, 5/6. The last part, union Y dash. Whole thing dash, again using the formula I can write 1 minus probability of X union Y. We found the value for union is 11/12. 1 minus 11/12. 1 I can write 12/12 minus 11/12. We get 1/12. Question number 3. A and B are two events of a random experiment. PA given as 2 over 7, PB dash is 1/4. Find PA dash and PB. PA dash. What's the formula? 1 minus probability of A. 1 minus 2 sevenths. I can write 1 as 7 over 7. When you simplify, we get 5 over 7. What is PB? PB is 1 minus probability of P dash. 1 minus PB dash is 1/4. 1 I can write 4 over 4. When we subtract, 4 minus 1 becomes 3. So the answer is 3/4. Question number 4. X and Y are two events of random experiment. It is given that probability of X is half, probability of Y is 1/3 and union is 5/6. Find the intersection. Probability X intersection Y. So what's intersection? According to the formula, I can write down probability of X plus probability of Y minus the union. I can change union to intersection, intersection to union. Probability of X given half, probability of Y given 1/3 and the union given 5 over 6. So I need to convert to the same denominator, that's 6. 3 times 2 is 6, so 3 times 1 is 3. How you get 6 from 3? Multiply by 2, so you get 2 here. Minus 5, 3 plus 2, 5. 5 minus 5 is 0. 0 divided by any number is 0. Now we found out the intersection is 0. Then they are asking thereby show that X and Y are mutually exclusive. So the intersection we found that's equal to 0 means there are no common elements for both X and Y. So therefore we can say X and Y are mutually exclusive events. So if we draw the diagram, Venn diagram, we can draw these two separately because there are no common terms. Question number 5. X, Y and Z are three events of a random experiment. If probability of X is 1/6, probability of Y is 1/9 and probability of Z dash is 2/3, intersection is 1/18 and X and Z intersection is 1 over 12. Find the following. Probability of X. Here there's another mistake. This should be X dash because X is given. Probability of X dash is what? 1 minus probability of X. What is probability of X? 1 over 6. 1 means 6 over 6 minus 1 over 6 becomes 5 over 6. Then probability of Y dash. Again we can write probability of Y dash is 1 minus probability of Y. Probability of Y is given 1 over 9. I can write 1 as 9 over 9 minus 1 over 9. We get 8 over 9. P, Z. Z dash is given. So how can we write down? 1 minus P Z dash. 1 minus 2/3. 1 I can write 3 over 3 minus 2/3. That becomes 1 over 3. X union Y. I can use the formula to find out the union. Union is equal to Px plus Py minus Px intersection y. Px is 1 over 6, Py 1 over 9, intersection is 1 over 18. So when you look at this one, what's the common denominator? That's 18. 6, 9, 18. The common denominator is 18. Multiply by 3, you get 3 here. Multiply by 2, this one, you get 2 minus 1. 3 plus 2, 5. 5 minus 1, 4. 4 over 18. When you simplify, you get 2 over 9. Then x union z dash. So what is x union z dash means? First we need to find out the union. We'll first find union for that. X union c. How can we find out union? We can find out using the given information. Probability of x union c is probability of x plus probability of z minus probability of x intersection z. Probability of x is 1 over 6. Probability of z is, we found, that's 1/3. What's x intersection z? X intersection c given as 1 over 12. So we'll use that value, 1 over 12. The common denominator is 6, 3, 12 is 12. Convert, 2 times 1 is 2. This is 4 times 3, 4 times 1 is 4. Minus 1, 4 plus 2, 6, 6 minus 1, 5. 5 over 12. We found out the union is this. So what is this one now? I can substitute this value. Again, I'll write down the question. Probability of x union z dash is equal to 1 minus probability x union z. Union c we found 5 over 12. Substitute 1, I can write 12 over 12. And then 12 minus 5 becomes 7 over 12. Now we'll look at how we can represent probabilities in a sample space diagram. So here in probability, we have two types of diagrams. One is called sample space diagrams. The other one is tree diagrams. We are doing it later. Now we'll take this example. Two unbiased identical coins A and B. So take two 1 rupee coins. So I'll take 1 rupee, another 1 rupee coin. Two identical. Identical means same type of coin. I'll label this as A, label this as B. And getting head as H, getting tail as T. Now when you toss 1 rupee coin, you can get two possibilities, H and T. Again, this coin also I can get two possibilities, H and T. So how can we represent this in a diagram? Now what are the outcomes we can get? When you consider both coins, you can get head from A and head from B. So that's HH possibility. Or you can get heads in A with head tail in B. So here I can, if this is first one is A, the second one is B. This means first head, second head. This one, heads in A, tails in B. I can get tail from the first one, A, and head from the second one, B. Or, what's the other possibility? Other possibility is tail and tail. That means both tails from A and B coin. So these are the 4 possible outcomes I can get. So how can I represent this in a diagram called sample space diagram? So we'll take 2 coins are there now. So we'll take x-axis for one coin and y-axis for the other coin. So when you take the diagram, we need 2 axes. I'll take this one as coin A, this side as coin B. You can take other way round as well. Then what are the possible outcomes in coin A? I can get head or tail. So I can mark like that the possible outcomes. What are the possibilities in coin B? Again, head and tail. So I can write H and T. And how you get the combined outcomes? When you refer this diagram, H with H. So this means both heads. What is this means? Head in coin A with tail in coin B. This one, tail in coin A with head in coin B. This possibility is both tails. So if I want to label this one, I can write this one is HH. This one is H with T. This one T with H. This one is T with T. So you don't need to label like this, but identify the possible outcomes. So these possible outcomes are here, and altogether how many are there? 4 possible outcomes. Now we'll look at example number 1. Let us consider the experiment of tossing a coin and rolling a tetrahedral die numbered 1 to 4 and recording the faces touching the table. Show the sample space as a set of ordered pairs on a grid and then represent it on a grid. First we need to write down and then show that in a diagram. Okay, what are the possible outcomes when you take tossing a coin? So tossing a coin, you can get heads or tails. A tetrahedron die, rolling tetrahedral die. You get 1, 2, 4. 1, 2, 3, 4. And what are the possibilities we can get? We can get as a sample space H with head with 1, head with 2, head with 3, head with 4. As well as we can get tail with 1, tail with 2, tail with 3 and tail with 4. So those are the all possible outcomes when you toss a coin and a tetrahedral die. Now we need to show this in a diagram called sample space diagram or a grid. So how can we draw that? We can take two axes. One you can take as the, I'll take the coin for this side, coin, and this is the die. What are the possible outcomes on the die? 1, 2, 3, 4. On the coin, heads or tails. So what are the possible outcomes? You can get, this is 1H or H1, 1T, 2H or HT, 2T, 3H, 3T, 4H and 4T. So this is the sample space grid. Then question number 2, it says 1 on the die. Find the probability of getting 1 on the die. Okay, so we'll find out. I'll use different colors. 1 on the die means only possibilities are these two. So I can highlight this or this. So what's the probability of getting 1 on the die? Altogether, how many possibilities are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 possibilities are there. Out of 8 possibilities, 2 possibilities are getting 1s. So I can write probability of getting 1 on the die is equal to 2 over 8. Simplify this, I can write as 1 over 4. Part B, so this is A. Part B, an even number on the die and tails on the coin. Probability of getting even and tail. Even number and a tail. Now we'll take another color for that. I'll take purple. Okay, even numbers are 2, 4. As well as you are getting tails. Tails with, you can get 2 or you can get 4. Now, how many outcomes are there? 2 possibilities out of 8. Again, I can write this is 2 possibilities out of 8. When you simplify, you get 1 over 4. Third part. Part C. 2 on the die. Probability of getting 2 on the die and heads on the coin. 2 and H. We'll take red one. 2 and H. So you have to take H as well as 2. So how many possibilities? 1 possibility for H and 2. Then we can write as 1 outcome out of 8. So that's the probability. Example number 2. There are 5 identical balls numbered from 1 to 5 in a bag. A ball is taken from the bag randomly and the number is recorded. Then the ball is put back in the bag with replacement, and again a ball is randomly taken for a second time. And this number is also recorded. Show the relevant sample space in a grid. Now when you take the bag, what are the numbers you can get? 1, 2, 3, 4, 5. So if we write down the sample space, you can get 1, 2, 3, 4, 5. And What's the next one? You're taking a ball and replace it back and taking another one. So same like the same thing happened second time. Taking another ball from the same bag. Find the probability. First you have to show the relevant sample space diagram. So how many sides are there? 2 sides. We can take one side as first time taking the ball. First ball. That means taking first time. What are the possibilities? 1, 2, 3, 4, 5. Then if you take this axis as second time taking the ball, second ball. Again you can get either 1, 2, 3, 4, 5. So what are the possibilities? You can get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 5, 2, 1, 2, 2, 2, 3. I'll put crosses. It's easy. 2, 4, 2, 5. Then this one 3, 1, 3, 2, 3, 3, 3, 4, 3, 5. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5. So those are the possible outcomes you can get. Then we are asked to find out these probabilities. Find the probability that the first ball is numbered 5 and the second ball is numbered 2. Identify the proper section. I'll take blue color. First one, 5. So 5 and the second one, 2. How many possibilities are there? Only one possibility. Out of how many altogether? 5 times 5. 1, 2, 3, 4, 5 times 5. You get 25 possible outcomes. So this is just one bag. 1 to 5 is just one bag. When you take 2 bags, you have to consider 25 outcomes. And what's the probability? So probability is out of 25, just one outcome. So 1 over 25. Second one, find the probability that the sum of the numbers on the 2 balls is 4. How can we get 4? So we need to identify the possible outcomes. I'll take red color one. I'll take red color one. The sum is 4. How can we get sum 4? 1 and 3. Then here with 2, I can get 2 with 2. With 3, I can get 3 and 1. So altogether 3 possibilities are there to get sum 4 out of 25 outcomes. So probability is 3 over 25. Now the fourth one, find the probability that the same ball is taken on both occasions. So now when you take this diagram, same occasion you are getting the same outcome. Same outcome means you can get 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So how many outcomes altogether? 5 outcomes out of 25. I can simplify and write down 1 over 5. 5 times 1, 5 times 5. 1 over 5. The next one, are the events in 2 and 4 mutually exclusive? 2 and 4. That means blue one with black one. Are there any common terms? Blue one with black one. There are no common terms. So what can you say? Mutually exclusive. So here we can write no common elements in 2 and 4. 2 second part and the third part. Therefore, mutually exclusive. I'll write here mutually exclusive. Sixth part. Find the probability that the sum of the numbers on the two balls taken is greater than 7. So we need to identify the region. Greater than 7. So if you take 1 and 5, the maximum is 6. So you can't take that. 2 with 5, maximum is 7. Greater than 7 is not included. So what's the number? 3 with 5, 8. Yes, you can get greater than 7. 3 with 4 can't. With 4 with 4, 4 with 5, 9, and 4 with 4, 8. And what else? With 5, you can get 5 with 5, 5 with 4. And 5 with 3, you get 8 as well. So, how many numbers altogether? 1, 2, 3, 4, 5, 6. 6 numbers greater than 7 out of 25. So, the probability is 6 over 25. Are the events in 3, third part and fourth part are mutually exclusive. Third part and fourth part. That means red color one and the black one. Red and black. Here red and black. I can see here this element is common. Red one and black one is there. So that means not mutually exclusive. So we can write common terms are there. Common outcomes are there. Therefore, not mutually exclusive. Exercise 30.3. A fair die numbered from 1 to 6 is rolled and an unbiased coin is tossed at the same time. The side on top is recorded in each case. Consider this experiment. Show the sample space in a grid. What are the two possible outcomes? What are the two possible events? Two possible events are throwing a die and a coin. When you take the coin, what are the possibilities? Head and tail. When you take the die, it's 1 to 6 labeled. So we can write 1, 2, 3, 4, 5, 6. And what are the outcomes? You get 1H, 1T, 2H, 2T, 3H, 3T, 4H, 4T, 5H, 5T, 6H and 6T. So that's the sample space diagram. Use it to find the probabilities of the following events. First one, it says getting one on the die and the heads on the coin. 1 on the die and heads on the coin. I'll take different color. I'll take blue. 1 and hit. So only one possibility. So what's the probability? 1 over 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 and 6. Altogether 12 outcomes are there. So probability is 1 over 12. Second part, getting an even number on the die and heads on the coin. Even and head. Head means this one. Even numbers are 2, 4, 6. So you get 2, 4, 6. That means 3 possibilities out of 12 outcomes. When you simplify, you get 1 over 4. Third one, getting tails on the coin. Getting tails means you can get this whole part. So how many outcomes are there? 1, 2, 3, 4, 5, 6 outcomes out of 12. When you simplify, you get half. Question number 2. 2 fair dice numbered from 1 to 6 are rolled simultaneously and the side shown is recorded. Consider this experiment. Show the sample space in a grid. Use it to find out the probabilities. So both are dice. So I'll take blue color so we can draw the diagram first. I'll take one axis as the first die, die 1. And this one is the second die, die 2. Both dies you get labeled 1 to 6. So what are the possibilities? I can get these possibilities when you think about 2 dice. Altogether how many? 6 times 6. Altogether we get 36 outcomes. And we'll try to answer part B. First part, the sum of the two numbers being 5. What are the numbers you get when you add the two numbers is equal to 5? 1 with 4, 2 with 3, 3 with 2, 4 with 1. 4 possibilities are there. So what's the probability? 4 over 36 altogether. Simplify, 4 times 1, 4 times 9, 1 over 9. Second one, the sum of the two numbers being greater than 10. Greater than 10, greater than 10 means 1 with 6 maximum 7. Here 2 with 6, 8, 3 with 6, 9, 4 with 6, 10, 5 with 6, you get 11. You can take that one. And 6 with 6, 12, and 6 with 5, 11. Altogether, how many outcomes are there? 3 outcomes out of 36. So I can write 3 out of 36. When you simplify, you get 1 over 12. Third one, the two numbers being the same. What are the possibilities? You can get two numbers are the same. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 and 6, 6. So altogether 6 numbers are there out of 36. When you simplify, I can write as 1 over 6. Next one, the two numbers being the same. So that's the part we did. So here, this should be third part. Last part, getting 3 on the first die. So first die is here, getting 3. So how can we mark that? I'll take red color. 3 on the first die means I can get all possibilities like this. So 1, 2, 3, 4, 5, 6 possibilities are there out of 36. When we simplify, you get 1 over 6. Question number 3. A bag contains identical beads. There are 3 red beads, 1 1 blue bead and 2 yellow beads. These are labeled R1, R2, R3 and B and Y1, Y2. A bead is taken randomly, its color is recorded and then put it back in the bag. A bead is randomly taken from the bag again and its color is recorded. Show that the sample space in a grid. So for this one, again I can take the 2 axes. I'll take one axis as first bag, first time, first ball or something, first bead, and this is the second bead. What are the colors here? R1, R2, R3, B and Y1, Y2 here. So same thing on the other side. R1, R2, R3, B, Y1 and Y2. So what are the possible outcomes? These ones. This means R1, 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 R2. So like that, you can mark all these possibilities. So altogether, how many outcomes are there? One side, 1, 2, 3, 4, 5, 6. The other side also 6. 6 times 6, you get 36 outcomes. So we are marking 36 outcomes like this. So this is the sample space grid. Then we'll use this one to find out the probabilities. First part, the first bead being red and the second bead being yellow. Red this side and yellow on this other side. So R1 with yellow, R2 with yellows. So I can take these 3. R1 with yellow as well as R1 with this yellow also I can get, because it says first bead is red and the second bead is yellow. So I can draw this as well. So I can altogether draw this whole part. I'll erase this line and this whole thing, I'll mark it again. The outcomes, those are these outcomes. No? So altogether 6 outcomes are there out of 36. So I can write 6 out of 36. When you simplify, 1 over 6. Both beads being red. Second part, both beads being red means which part we have to take? Red and red all together, this whole part. How many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 outcomes. 9 out of 36. 9 times 4, 36. So you get 1 over 4. Both beads being the same color. We'll take another color. Red. Same color. So I can get red with red. So that means this part. Blue with blue. This part. And yellow with yellow. This part. Altogether, how many outcomes are there? 9 here, 10, 11, 12, 13, 14. 14 outcomes out of 36. Simplify, divide by 2. You get 7 over 18. Fourth part, getting at least one blue bead means either one or more blue beads. But here only one bead from one bag. One blue bead. So we'll take light blue color. Okay, so identify this region. At least one blue bead. So you can get one blue from the first bag. So that means this whole part. Or you can get blue from the second bag. You can get this whole set as well. So all together, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 beads are there out of 36. So the probability is 11 over 36. Fifth one, write all the pairs of mutually exclusive events in the above question 1 to 4. Now we'll identify 1 and 2. 1 is which color we took? We'll identify. First one we did red and yellow. That's pink color. Pink color and this one blue, like that. We know the colors. Now we'll see whether there are common elements. Common elements means not mutually exclusive. Now when you identify this one, the pink color one with orange color one, mutually exclusive. So that means one with, I'll take this one. Pink color one is the first one. One with orange. Orange is third one. 1 with 3, mutually exclusive. And also 1 with this blue color also, there's no intersection. 1 with light blue, we took the fourth one. 1 with 4. What else? And the blue color one. Blue color one is also mutually exclusive with the first one. 1 with blue color one is the second one. And 1, 2, 3, 4. Then 2 with, that means blue color and orange color, not mutually exclusive. Blue color with this one, mutually exclusive. No common elements with this one. So blue color is second one with fourth one. Second one and fourth one mutually exclusive. and that's then third and fourth. Third and fourth means orange color with blue one. Orange color with blue one, not mutually exclusive because this element is common. So these are the mutually exclusive events. Question number 4. There are 5 roads labeled A, B, C, D, E that meet at a junction. Here it is possible to enter or exit from any road. Draw a grid showing all possible ways in which a person can enter and exit and find the probabilities of the following events. Assume that all the possible outcomes are equally likely. Entering from A and exiting from B. Entering from A and exiting B and exiting from D. Entering from E. So here, what are the possible outcomes for all these? Entering and exit. Enter and exit. 2 possible outcomes are there. In this question, we'll take the 2 sides as one is enter, the other one is exit. So, what are the roads? You can exit from A, B, C, D, E, as well as you can enter from A, B, C, D, E. So these are the possible ways of entering and exiting from the junction. Altogether, how many ways are there? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 times 5, 25 possibilities are there. Now we'll take the first one. Entering from A and exiting from B. Entering and exiting from B means only one possibility. So what's the probability? 1 over, first one, 1 over 25. Second question, entering from A or B. Entering from A or B and exiting from D. We'll take another color. I'll take blue. Entering from A or B and exiting from D. Exit from B. So you get these 2 possibilities. 2 possibilities out of 25. Then the third part, entering from E. Entering from E means not mention about the exit one. So you can take entering from E means you can take this whole part. So what's the probability? 1, 2, 3, 4, 5. 5 out of 25. When you simplify, you get 1 over 5. Last part, I'll take black. Entering and exiting from different roads. So different roads means if you take A, you can't take A again. So you have to take this part. If you enter with B, you can't take B. So you can take A and the other ones. When you take C, you can take these 2, but not this one. When you take D, you can take all C, but not D. E means you can take up to here. Now count how many are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 are there out of 25. 5 times 4, 5 times 5. So the probability is 4 over 5. Question number 5. A plant has 4 red flowers and 3 yellow flowers of identical shape and size. 2 butterflies A and B come to the flowers to drink nectar. It is possible for both to drink nectar from the same flower at the same time. Draw a grid of the sample space showing all the possible ways the butterflies can pick flowers to get nectar and find the probabilities of the following events. Assume that the butterflies pick flowers randomly. So we need to draw a sample space grid. So what are the two axes? When you take flowers, you get 4 red flowers. So I can take R1, R2, R3, R4 and 3 yellow, Y1, Y2, Y3. And that's all. And 2 butterflies are A and B. So I can write this is butterfly A and this is butterfly B. What are the possibilities? Here also red 1, red 2, red 3, red 4, Y1, Y2, Y3. What are the possibilities? These are the possibilities and I can find out the probabilities easily when you draw the sample space diagram. How many possibilities are there altogether? One side, 1, 2, 3, 4, 5, 6, 7. 7 times 7, 49 possible outcomes are there. 49 possible outcomes are there. Now we'll try to answer the following questions. First part, butterfly A picking a red flower and butterfly B picking a yellow flower. Which outcomes are suitable? When you take butterfly A picking red and butterfly B picking yellow. So you can get this set. So here we miss this one. You are getting this whole set. R1, R2 with this one yellow color. So all together 4 times 3, 12 outcomes are there out of 49. Then the second part, both butterflies picking flowers of the same color. So same color means you can get red, this set. Same color Y means this set. So altogether how many? 1, 2, 3, 4, 4 times 4, 16. 16 plus 9, you get 25. So what's the probability? 25 over 49. The next part, third one, both butterflies picking flowers of different colors now. Different colors, we'll take red one now. Different colors means if this is red, that should be yellow here, yellow this part. If this is yellow, this should be red. So these two sets. Here 4 times 3, 12 and 3 times 4, 12. 12 and 12, you get 24. So what's the answer? 24 out of 49. Last part, both butterflies picking the same flower. Same flower means red one with red one, R2 with R2, R3 with R3. So same color means these possibilities. So altogether how many? I can mark like this also. This set, sorry, this one, 1, 2, 3, 4, 5, 6, 7. 7 outcomes are there. 7 out of 49. You can simplify and write 1 over 7. Now we'll look at what are independent events. We'll take a small example, tossing 2 coins at once. So 2 coins are there. So 1 coin and another coin. Coin 1, coin 2. What are the possible outcomes? You can get head, tail from the first coin, head, tail from the second coin. So when you toss these at once or separately, getting head from the first coin is not affected by the second coin, or getting tail for the second coin is not affected by the first coin. So both are we call independent events. So if the result is not involved with the other event, we call those are independent events. So if 2 events A and B are independent, you need to know probability of A intersection B is equal to probability of A times probability of B. So you need to know this formula when you see any 2 independent events. You can apply this formula. Another example, if you take 2 bags, taking beads from one bag is not affecting by the taking beads from the second bag. So those are independent events. When you see independent case, straight away you can apply this formula. Now we'll look at example 1. X and Y are 2 independent events and the probability X is given 1 over 3 and probability of Y is 1 over 4. Find the intersection. What it says, if the 2 events X and Y are independent, then you can write this one as Px into Py. Substitute the values, 1/3 times 1/4. You get 1 over 12. Then you are asked to find out the union, X union Y. Can you remember the earlier formula? That's equal to Px plus Py minus the intersection. Substitute. Px is 1/3, Py is 1/4 and the intersection we found 1 over 12. We'll find out 12 is the common denominator. You have to multiply by 4, multiply by 3 and you get 4 plus 3 7, 7 minus 1 is 6, 6 over 12 is same as 1 over 2. Example number 2, the probability that candidate A will pass an examination is 1/5. So I'll write down pass, probability of pass is 1/5. Probability that candidate B will pass, this is candidate A will pass, B will pass is 3 over 10. Assume that these events are independent and find the probabilities of the events below. both of them passing. Both of them passing means you are asked to find probability of A pass and means intersection with B pass. If the two events are independent, straight away we can write this is same as probability of A pass into probability of B pass. B passing the exam and A pass the exam. What's the passing probability of for A? That's 1/5. Passing probability for B is 3/10. When you multiply, you get 3 over 5 times 10 is 50. Second part, one of them passing. One of them passing means either A pass or B pass. What's the symbol? Union. So they are asking union for that. So use the formula. You can use probability of A pass plus probability of B pass minus probability of A pass intersection B pass intersection. Then substitute the values. We can substitute A passing probability is 1/5, B passing probability is 3/10, and we found out the intersection is 350 over 50. Then the common denominator we can take as 50, multiply this by 10, this by 5. 5 times 3, 15, minus 3, you get 10 plus 15, 25, 25 minus 3, you get 22. 22 over 50, when you divide by 2, 11 over 25. Example number 3, two unbiased identical coins are tossed simultaneously. Let us represent the sample space of this random experiment in a grid. Take the event of the first coin being heads as A. Take the event of both the coins showing the same side as B, and you are asked to check whether A and B are independent. So we'll first try to draw the sample space grid. We can take first coin on this side and the second coin on the other side. What are the possible outcomes? H and T. Here also H and T. And these are the 4 possible outcomes. So what is A? A we will mark in this color. A is event A of the first coin being heads. First coin being heads means this is event A. Then the second one, event of both the coins showing the same side as B. Same side as B means H with H, T with T. So we'll take that one in red color. So which one is event B? This one. So this is event B. Okay, so check whether A and B are independent. So we need to identify whether A and B are independent. So what's probability of A? Probability of A means 2 possible outcomes out of 4. What is probability of B? Here also when you take B set, 2 possible outcomes out of 4. I can simplify this one as half, this is also half. Now we'll take intersection. Probability of A intersecting with probability of B. That means common region for both A and B. We can see one is intersecting each other. So 1 out of 4. Now left hand side is this. We want to multiply PA and PB and see whether you are getting the same as intersecting value. PA is half and PB is also half. Half times half, you get 1/4. Now what can you say? Probability of A intersection B is same as probability of A multiplied by probability of B. When you multiply, you get the same answer. So that means A and B are independent events. Exercise 30.4. X and Y are independent events. Probability of X is given half, intersection is 1/3, and you are asked to find out PY, probability of getting Y. So I'll do the question. First thing, you are given probability of X is half. How can we identify whether these are independent? We can use the formula, but already given this is independent. So you can use this formula straight away. So if you want PY, you can make PY as a subject of the formula. Intersection is 1/3. PX is half. And you want to find out PY. So what we do? To get PY, I need to multiply this by 2. So when I multiply this by 2, both sides by 2, I get 2/3 as PY. Second one, find the union. PX union Y is same as probability of X plus probability of Y minus X intersection Y. What's probability of X? Half. Probability of Y we found 2/3. And the intersection is given as 1/3. So we can write intersection is 1/3. So what you get? What's the common denominator? 2 and 3. You get 6. 3 times 2 is 6. So you get 3 here. So here 6, 2 times 2, 4, and multiplied by 2, 2 times 1 is 2. So what's the answer? 3 plus 4, 7, 7 minus 2, 5. So the answer is 5/6. Question number 2. An unbiased coin and a fair die numbered from 1 to 6 are tossed simultaneously. Represent the sample space relevant to this experiment in a grid. The second part, take the event of the coin showing heads as A and the event of the die showing the number 4 as B. Show these events on the grid and find the probabilities of the events below. So first thing, we have to draw the diagram. So when we draw the sample space diagram, what is the first side? We can take the numbers, the fair die. Die on one side and the coin on this side. So die, what are the numbers? 1, 2, 3, 4, 5, 6. And what about the coin? Coin, you get 2 sides, heads or tail. So what are the possible outcomes? We get these outcomes. Altogether 12. 12 possible outcomes are there. Then it says, take the event of the coin showing heads as A. Showing heads as A. That means this one is event A. And what's the event B? Showing the number 4 as B. Showing the number 4 as B. I'll take another color. I'll take red one. So this one is B. Now we'll try to answer the questions. Probability of A. So probability of A, altogether 12 outcomes. 1, 2, 3, 4, 5, 6 are there. So 6 out of 12. You can simplify and write half. Second one, probability of B. B has 2 outcomes. 2 outcomes out of 12. When you simplify, you get 1 over 6. Third one, intersection. Intersection means common region for both these two sets. What's common? Only one is common. 1 out of 12. Then union, you can use the formula. Probability of A union B. Using the diagram also we can find. We don't have to use the formula. So this everything together 1, 2, 3, 4, 5, 6, 7. 7 outcomes are there out of 12. So what's the union? Union is 7 over 12. Question number 3. A bag contains 3 red beads and 2 blue beads, all of which are otherwise identical. A bead is taken out randomly and its color is recorded and then it is put back in the bag. A bead is randomly taken out again and its color is recorded. Find the probabilities of the following events. So we'll draw a sample space diagram to answer this question. What are the beads? 3 red beads. I can take R1, R2, R3. And 2 blue beads. B1, B2. And here the other bag. This is first bead. We'll take first bead from the first bag. And then taking again. So you get the same outcomes. R1, R2, R3, B1, B2. Now I can mark all together how many possibilities? 5 times 5. 25 possibilities are there. First part, both of the beads being red. So which part? Red color. So you get this region. So altogether how many outcomes? 3 times 3, 9 outcomes out of 25. The second one, the first bead being blue and the second one is red. First one is blue and the second one is red. I'll take now light blue. First one is blue and the second one is red, means this whole region. Blue with red. No. First bead being blue and the second one is red, means this region. So altogether how many? 6 beads. 6 outcomes are there out of 25. 6 over 25. Third one, I'll take another color. I'll take red one. The first bead being red, first one red, and the second bead being blue. So 3 reds with this one, you get this part. So 6 out of 25. Then the last part, both beads being blue. I'll take black. Both beads being blue means this blue with this blue, you get 4 possibilities. 4 over 25. Now we'll look at how we can draw tree diagrams. Earlier we did how to draw sample space diagrams. Now we'll see why we need tree diagrams. When you take tossing 3 coins at once, what happens? You need 3 axes. But in the sample space diagram, maximum 2 sides, x-axis and y-axis, only maximum 2 sides. But what happens when you get more than 2 events? You can't draw a sample space diagram. Then we need to know another type of diagram. So we can use tree diagrams. But in your syllabus, all the events are strict to 2 events. But main thing why we are drawing a tree diagram, when you get 2 or more than 2 basically events, we need to have another axis in sample space, so that's not obvious. That's why we are drawing tree diagrams. When you get more than 2 events, definitely you have to draw a tree diagram. Now we'll take an example to show a tree diagram. Example 1. An unbiased coin is tossed twice and each case the outcomes is recorded. Draw the relevant tree diagram and find the probabilities of the following events. So in this case, if you take 2 coins, we'll take the first coin. First coin, what are the possibilities? Head, tail. Second coin, what are the possibilities? Head, tail. In the tree diagram, what we do, we take this one other way around. So there are branches, 2 branches. In a tree, you get branches. So that's the basic idea about tree diagram. So when you take the first coin, this is the first coin, you get 2 branches. First coin, 2 branches, you can get head or tail. Then we have to connect the second branch. Second coin, you have to connect to this branch as well as to this branch. So what you get? So when you connect this one here, you get a diagram like this. So first one, you get head, tail. So we can write the label as somewhere here, first coin. Then when you connect the whole thing here, what you get? You get another 2 branches, H, T. And the same thing when you plug here, you get H, T here as well. So when you take the full diagram, I can label this one as second coin. Now we can show the probabilities on top of this branch. What's the probability of getting head? Half. So we can write down the probabilities on top of the branch. So every time the probabilities are equal, so you can write half here. So this is a full tree diagram. What are the possible outcomes? Now how we refer the diagram? Along the branch here, when you take this branch together, you are getting first time head, second time head. So I can write the outcome as HH. When you take this branch, first one head with second one tail, HT. When you take this branch, first time tail, second time head. And this branch, both tails, that means first time T and second time T. And also when you consider a tree diagram, along the branches we multiply. We take and probability of getting head and probability of getting head. If you want to find out the probabilities, we multiply these two. So you can write half. If you want probabilities, I'll write probabilities of these is equal to half times half. If you want this branch, that's also half times half. This one, half times half. And this is also half times half. When you simplify, you get 1/4 for each one. Now we'll try to answer the following questions. We need getting heads both times. Getting heads both time is this branch. That's this branch. We found out that this branch is 1/4. And the next one, getting the same side both times. Getting the same side means either head head or tail tail. So we can take two branches, head head or tail tail. So what we do? We have different branches, so we can add the probabilities. This branch is 1/4. The other branch is also 1/4. 1/4 plus 1/4, 2/4, or simplify this, you get 1/2. Third one, getting tails at least once. At least once means either one tail or more than one tail. So what are the possibilities there? You get all these possibilities. I'll take blue color, light blue. At least one tail means you can get this branch and both these branches. So altogether this whole thing. So how can we find out the probabilities? You have to add the values for each branch. So this one is 1/4. This is also 1/4. And this is also 1/4. So 3/4 are there. Or there's an easy way. You are asked to find out at least one tail. So you can subtract from 1. So you need this branch. We know the full thing is 1. 1 minus this branch also possible. 1 minus, I'll write here. Instead of this, you can do 1 minus probability of getting both heads. 1 minus 1/4 is 3/4. That's also possible. Now, next part, here this should be fourth one. Getting heads the second time. Getting heads in the second time means here either HH or TH. Only two possibilities are there. So, how can we do the fourth part? Getting head means HH or TH. You can't take the other one. HT. HT means second time tail, first time head. So when you add these to 1/4 plus 1/4, you get 2/4 or half. So that's the probability of getting heads the second time. Exercise 30.5. A box contains 4 red pencils and 2 black pencils. A pencil is taken from the box at random and returned back to the box after its color is recorded. And then another pencil is taken out of the box. Depict the sample space as a tree diagram and hence find the probability that both pencils are red, the 2 pencils are of opposite colors and the 2 pencils are the same color. So first we'll draw the tree diagram. So when you take the first box, what are the colors? Red and black. In this case, no need to label as red 1, red 2, red 3 like that. You need to just show what are the different colors. So here, when you take the first box, I'll write box 1. You can get red or black pencils. How many red ones are there? 4. Altogether 6. The probability is 4/6, or I can write as 2/3. Black ones, 2 black ones out of 6. I can write as 1/3. So that's the probability. Now again another box is there, same type. That means same outcomes are there. So we can draw the other box again, red, black, red, black. Same probabilities are there, 2/3, 1/3. 2/3 and 1/3. And also in a tree diagram, there's a property. When you take one tree, the sum of probabilities are equal to 1. So 2/3 and 1/3 becomes 1. So remember that when you draw a tree diagram, the sum of the branches add up to 1. Here 2/3 and 1/3 here. Again you will see 3/3 or same as 1. So here also 2/3 plus 1/3 becomes 3/3, that's equal to 1. Now we'll try to answer the questions. Both pencils are red. So we'll try to mark the branches. Both pencils are red means you have to select this branch. So what you get? Red and red. So how we find out the probabilities? We can multiply the probabilities. So here red and red. 2/3 and 2/3 again. 2/3 multiplied by 2/3. What you get? 2 times 2, 4. 3 times 3, 9. 4/9. The second one. The 2 pencils are of opposite colors. What are opposite colors? You can get red and black. So now mark the branches. I'll take black color. You can get red with black or black with red. So those are different colors. So when you take this branch, how can we find out the probability? This is 2/3 multiplied by 1/3. This branch, 1/3 multiplied by 2/3. So when you want the total probability, you need to add these two together. So what is this one? 2/9. Here 2/9. So we can add these two together. 2/9 plus 2/9 becomes 4/9. Last part. The two pencils are of the same color. So how can we find out the same color? That means either red red or black black. So we'll find out the region. Red red, this part, or black black, this one. What's the probability of getting red red? We found that in the previous part, 4/9. So we'll take that one, 4/9, plus getting black black. What's getting black black? Means 1/3 into 1/3, you get 1/9. So we can add these two together. 4/9 plus 1/9 becomes 5/9. So the answer is 5/9. Question number 2. Sarath and Sunith work at the same workplace. They use the bus for their daily travel. The probability that Sarath is late to work is 1/3 and that for Sunith is 1/4. Depict the relevant sample space in a tree diagram and hence find the probability that both are not late. Only one person is late. So first thing, think about Sarath. What are the possible outcomes? He can get late or not late. So here we can write two possibilities are there, late, not late. What's the probability of getting late? It's given 1/3. Then what's this probability? I told you when you add the branches, you have to add the two probabilities. You are getting 1. So 1/3 is there. Then to get 1, this should be 2/3. Now we'll think about Sunith. Sunith also same possibilities. Sunith got same two possibilities, late and not late. But the probabilities are different. What's the probability of getting late for Sunith is 1/4. Now you can find the probability of not late. 1/4 is there. You need 3/4 to get 1 here. 1/4 for late probability, then this becomes 3/4. So this is the full diagram. Now we'll try to answer the questions. Both are not late. Both are not late means not late, not late. So this branch we have to take. So what is this branch? 2/3 and 3/4. So we can multiply 2/3 into 3/4. Can you see? When you multiply, these 3 get cancelled out. And this one you get 1 and 2. Final answer is half. Part 2, only one person is late. It can be either Sarath or Sunith. We'll take light blue color. One person late means if Sarath is late, Sunith is not late. If Sarath is not late, Sunith is late. So these two branches we have to take. What is this branch? 1/3 into 3/4. I'll do it here. 1/3 into 3/4 is this branch. What about this branch? 2/3 and 1/4. So we need to multiply and add the two probabilities. Now try to simplify. 3 get cancelled out. Here this 2 get cancelled out with this 4. You get 2. Or without cancelling, you can do this easily. Later we'll simplify because the common denominator is 12. So I can take 12 as the common denominator. This one is 3 and this one is 2. 3 plus 2 is 5. So the answer is 5/12. Question number 3. The probability that the shooter in a netball team shoots the ball correctly is 3/5. Draw the sample space of the two shots in a tree diagram and find the probability of shooting correctly both times and shooting correctly once. So we need to draw a tree diagram. So what are the two events? You can get correctly first time as well as correctly second time as well. So here I can divide this first time and second time. What are the possible outcomes when you shoot first time? It can be correctly or not correctly. Second time also you can get correctly or not correctly. So this one correctly, not correctly. What's the next step? You have to write down the probability. So what's the probability of shooting correctly? It's given 3/5. How can we find out this probability? Remember that when you add these two, you are getting 1. So 3/5 is there. This should be 2/5. Now fill the other gaps. 3/5 here, 3/5 there, 3/5 here. Then not correctly 2/5. This is 2/5 and this is 2/5. Now we have the tree diagram. Now using that diagram, we'll try to answer the first part. Shooting correctly both times. Identify the region. Both correctly means correctly and correctly. So this is the correct branch. How can we find out the probability? 3/5 and 3/5. Multiply. So 3/5 into 3/5, you are getting 9/25. Part 2. Shooting correctly once. What are the possibilities? Shooting correctly once. That means first time correctly and second time not correctly. Or first time not correctly and second time correctly. So those are the two branches for this question. So part 2, we can write down correctly and not correctly. That means 3/5 into 2/5 plus other branch is 2/5 and 3/5. So 25 is the common denominator. 3 times 2 is 6 here. 3 times 2 is 6. 6 and 6 becomes 6 plus 6, 12. So 12/25 is the answer. Miscellaneous exercise. Question number 1. In a survey of 25 students conducted to see who likes to drink tea and coffee, it was found that 17 students like to drink tea, 15 like to drink coffee and 10 like to drink both tea and coffee. draw a Venn diagram illustrating this information. Can you remember how to draw a Venn diagram? So they are asking probability questions using Venn diagram now. We'll first try to draw the Venn diagram. Okay, what are the sets? It says tea, like tea and coffee means 2 sets are there. So you need to draw 2 circles, tea and coffee. And then 25 students are there altogether. So we write 25 above. What's the next one? It was found that 17 students like to drink tea. 17 likes to drink tea and 15 like to drink coffee. 15 here. 10 like to drink both tea and coffee. So this is 10. Now try to fill the other gaps. The whole thing is 17, this is 10, this becomes 7. Whole thing is 15, this is 10, this becomes 5. Then when you add all together, you are getting 25. 10 plus 7, 17. 17 plus 5, you get 22. 3 should be there outside the 2 circles. Now that's the full Venn diagram. Now we'll try to answer the questions. Use it to find out the probabilities. Likes to drink only tea. Only tea, which region? So this region, 7. 7 out of 25. Second part, likes to drink only one of these 2 types. Either tea or coffee. So 7 plus 5 becomes 12. 12 divided by 25 is the probability. Third part, likes to drink either tea or coffee means inside the 2 circles. 7 plus 10, 17. 17 plus 5, 22. So what's the probability? 22 over 25. Last part, does not like to drink either tea or coffee means outside. Outside how many? 3. 3 out of 25. Question number 2. In a mixed school, each student who studied in the biological stream and in the mathematics stream has to take either exam P1 or P2 below is the actual classification of the 100 students in the 2 streams. If a student is picked randomly, find the probability that the student is a girl. Here, from the table, you can find out the probabilities. A girl, how many girls are there altogether? You need to add and see. So here, when you take girls, that's this side, you have to take the total. 10 plus 5, 15 there. What about here? Here, girls, 30 plus 10, 40. And how many altogether? We'll add all columns and rows and find out the total. 20 plus 5 is 25 here. 15 plus 5, 20. So what's the total here? Total here is 100. 100 students are there. When you take column wise total, you are getting 5 here, 75 and 25. Now we can answer easily. A girl. How many girls altogether? 15 here and 40 here. 15 plus 40, 55. So what's the probability of getting a girl? 55 over 100. You can simplify, divide by 5 and you get 11 over 20. Next one, following the mathematics stream. Mathematics stream, how many altogether are there? 25 students. 25 students out of 100. Simplify, you get 1/4. Doing exam P1. P1 means altogether these two. 15 plus 25. 40. So 40 students out of 100. So what's the probability? 40 divided by 100, and you can simplify further. You get 2/5. Fourth part, a boy following the mathematics stream and doing exam P2. A boy following mathematics stream. Mathematics stream, boys, as well as following P2 exam. So how many? 5. 5 boys are there out of 100. Simplify that. 1/20. Last part. Given that the student is a girl. So that means out of girls, what is the probability of her following the biological stream? So out of girls, 40 and 15 altogether, 55 girls are there. So out of 55 girls, how many are in the biological stream? How many in the biological stream? Here we can find out using this 10 and this 30. 30 plus 10 is 40. So the probability is 40/55. Simplify further, divide by 5. You get 8/11. Question number 3. Following is a quote from an advertisement. Everyone in 7 of the tickets in this lottery is a winning ticket. Hearing this, a person purchased 2 of the tickets of this lottery. Draw the relevant tree diagram and find the probabilities. We'll try to draw the tree diagram. A person purchased 2 of the tickets. So from that, you can take 2 branches, and one is winning and the other one is not winning. And what's the first one? First ticket. And the second one, we can call it second ticket. Branches are winning, not winning. Again, this one winning, not winning, winning here, not winning. Now we'll try to fill the probabilities. Everyone in 7 of the tickets in the lottery is a winning ticket. So that means 1/7 is the winning probability. So what's the losing probability? 6/7. Now fill the probabilities there. 6/7, 6/7. So this is the tree diagram. Now using this tree diagram, we can answer the following questions. First part, both tickets being winning tickets. Which branch we have to take? Winning, winning. Both tickets winning means this branch 1/7 times 1/7. You get 1/49. Second part, at least one of the tickets being a winning ticket. At least means either one or both tickets are winning tickets. Easily we can find out using not winning chances. So here I can write 1 minus probability of not winning both times. 1 minus. Not winning means 6/7 into 6/7. When you simplify, you get 1 minus 36/49. Convert to the same denominator. I can write 49 over 49 minus 36. 13 over 49. Question number 4. A circular disc as shown in the figure is divided into 3 equal sectors. 2 sectors are painted white and the third is painted black. A pointer at the center is free to rotate. The point is given a spin and the color of the sector at which the pointer stops is recorded. Draw a tree diagram for the 2 such spins and hence find the probability that the pointer stops in a white area in both instances, a black area at least once. So 2 possibilities are there. So here it says a point at the center here, spin, the color noted. 2 such spins. 2 such spins means spin 1, spin 2. What are the possibilities? White, black. So you need to draw only 2 branches. Even though there are 2 whites, we consider as white. Black, white. No need another white branch. Black, white. Black, white. Now fill the probabilities. Black this is equally divided now. 1 out of 3, 1/3. So how many whites? 2/3 are there. 1/3, 2/3, 1/3 and 2/3. Now we can answer the questions. First part, a white area in both instances. That means white and white. We can multiply 2/3 into 2/3. 4 over 9. Second part, a black area at least once. At least once means either one black area or twice. So here when you take this one minus both white is at least one black. So we found out both white, 1 minus that answer becomes at least once. 5 over 9. Question number 5. 10% of the candidates who applied for a job qualified through a competitive examination. Of those who qualified, 60% were selected in the first round. Find the probability that a randomly picked applicant is selected in the first round. So we can draw a tree diagram there. When you take candidates, 10% qualified for the job. And out of that, 60% were selected in the first round. So we'll take qualified ones. So here, qualified. Yes or no. After you get qualified, 60% were selected in the first round. So here, the second one is first round, selected and not selected. Here you don't have to draw another branch there because if you are not qualified, you can't go to the next step. Now we'll try to complete the diagram by putting the probabilities. 10% of the candidates who applied for a job qualified. 10%. So 10 over 100 gets qualified. So when you simplify, 1 over 10. So not qualified means 9 over 10. Out of qualified ones, 60% were selected in the first round. 60%. 60 over 100. When you simplify, what you get? 0, 0 get cancelled out. Divided by 2, you get 3/5. Selected for the first round. So not selected means 2/5. Now they are asking, find the probability that a randomly picked applicant is selected in the first round. So probability of getting selected for the first round is equal to only one branch. Which branch is there? You have to select this one. So that means 1 over 10 times 3/5. You get 3 over 50. Question number 6. There are 4 choices for each question in a multiple choice question paper, out of which only one answer is correct. A student who is unsure of the answers for 2 of the questions chooses random answers. Draw a tree diagram and hence find the probability that the same choice number is selected for both questions. Both answers are correct and at least one answer is correct. When you take one question, you get 4 choices. So 1, 2, 3, 4. 4 choices are there. Only one answer is correct. So what's the probability of getting correct answer? 1 over 4. So what are the possibilities you can get when you take one question? Correct or wrong. And it says 2 of the questions chooses. So that means this is the first question and you need to draw for the second question as well. This is also correct, not correct or wrong. Correct and wrong. The probability is 4 choices are there. One correct answer means 1/4 is the correct probability. Then wrong probability is 3/4. 1 minus that. Fill the other gaps. 1 over 4, 3 over 4. 1 over 4 here, 3 over 4. Now we'll try to answer the questions. First part, it says the same choice number is selected for both questions. Same choice means either you can get both correct or both wrong. Those are the 2 possibilities. So how you can find out the first part? That means 1/4 into 1/4 or means addition 3/4 into 3/4. So 1 over 16 plus 9 over 16, you get 10 over 16. When you simplify, you get 5 and 8. Second part. Both answers are correct. Both answers are correct. So what's the probability? So you have to select only that branch. Both answers are correct means 1/4 into 1/4. That's 1 over 16. Third part. At least one answer is correct. At least one answer is correct means you can get all 3 branches except both wrong. So easily you can find by 1 minus both wrong. Both wrong means 3/4 into 3/4. So 1 minus 9 over 16. I can write 16 over 16 minus 9 over 16 becomes 7/16. Question number 7. A and B are two government servants who work in the same office. They are entitled to a day's leave on any one of the 5 working days in a week. Assuming that each of A and B gets his leave at random on a grid, depict the sample space of all the possible ways in which they both can get leave during the 5 days of a week. Hence, find the probability of each of the following events. Now, they are asking for a sample space diagram. So, sample space diagram you can take as 2 axes. First one is a worker 1. We'll take A. A is the first worker and this is the second worker, and all 5 days, Monday, Tuesday, Wednesday, Thursday, Friday. Here also Monday, Tuesday, Wednesday, Thursday. Here I'll take TH for Thursday and Friday. What are the outcomes? These are the outcomes. 5 times 5, 25 altogether. Then we'll try to answer the questions. Okay, first part, A taking leave on Monday here and B on Wednesday. So you get one possibility out of 25. So the probability is 1/25. Second part, B taking leave on a day previous to A. So if it's Friday, B takes all the other days except Friday. So this part. If it's Thursday, previous days. Wednesday, you get these 2, and if it's Tuesday, he gets leave on Monday. So all together, how many outcomes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10/25. Simplify this. 5 times 2, 5 times 5. 2/5. Now take the third part. B taking leave on a day after A. So after A means if A takes Monday, he takes after Monday means any day here. If it's Tuesday, Wednesday onwards. If it's Wednesday, Thursday and Friday. If it's Thursday, he takes leave on Friday. So altogether how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10/25. Simplify, you get the same answer, 2/5. Last part, both taking leave on the same day. So that means if it's Monday for worker A, B worker also takes on Monday. So Monday, Tuesday, Wednesday. So likewise, this is the set 1, 2, 3, 4, 5. 5 out of 25. When you simplify, you get 1/5. We covered all the sections related to probability and we completed exercises and examples too. Mainly, you have to remember the 2 types of diagrams, sample space diagram and tree diagrams.